Hello, and welcome again to FlippedHarber for Algebra 2. In this video, we're going to be taking a look at section 1.3, square roots. Now before we get started with this video, I want to remind you, you're supposed to be taking notes right now. Now these notes should go into your notebook, and that means that they get to be used on the notebook quizzes. That means that I may be asking questions very specific to this video. It's going to be in your best interest to actually take these notes. Alright, let's get started. Our objectives for this lesson is to look at how to estimate square roots. We're also interested in looking how to simplify and then apply the four basic operations: add, subtract, multiply, and divide with square roots. Our topics for this lesson include the radical symbol itself, what you probably refer to as the square root, the radicand, that's the number under the square root, something that we refer to as the principal root, how to rationalize the denominator, looking at like radical terms, and then we're going to end by looking at some product properties and some quotient properties of square roots. Now after we cover all of that stuff, we're going to go over some examples. Now again, those examples absolutely must be in your notes. And you should already know what the homework for this section is. I try not to keep that stuff a secret, but I'll show what the homework assignment is for this section also. Alright, so let's start talking about square roots. Now you should all be pretty familiar with square roots. If I ask you what's the square root of 25, you should know that I'm looking for a number that multiplied by itself gives me 25. Now the square root of 25 works out nicely because 25 is what we refer to as a perfect square. Now if I ask for the square root of something that's not a perfect square, kind of the best thing we can do is plug it into our calculator and get an approximation. Now writing the square root of 45, that's an exact number. As soon as we punch it into a calculator or have a computer figure it out, that's an approximation. A lot of times we just want to leave it as the square root of 45 since it doesn't work out nicely. Now on the screen right now we see what we refer to as the principal roots. If I ask you what's the square root of 25, just give me the positive one. Don't give me the whole plus and minus stuff. If we actually want a negative, we'll put a negative in front of the square root. So if I want the negative, we'll put a negative like we see here in front of the square root of 81, and that's when you have to answer negative 9. If I want the plus and minus, we'll go ahead, put the plus and minus symbol in front of the square root. Okay? Now, one of the first things that we have to talk about is how to estimate square roots. I know, it's very easy for you to plug them into a calculator and just find out what the square root of 40 is equal to. But the idea here is that we want to have an idea going in what the square root of 40 is approximate to. So we actually take a look at our number 40, the radicand, and we figure out what are the perfect squares that are less than 40 and greater than 40. So in this case, the perfect square that's lower than 40 is 36. The perfect square that's higher than 40 is 49. Now we know that the square root of 36 is 6, the square root of 49 is 7. So that means that the square root of 40 is somewhere between 6 and 7. It's 6 point something. Well, that's not good enough. We've got to have at least one decimal place here. Usually the book asks for tenths place in the problem like this. So should I write down 6.5? Should I write down 6.7? Well, let's stop and think about this. 40 is closer to 36 than it is 49. It's only 4 away from 36, but it's a whole 9 away from 49. So we should choose a decimal that's closer to 6 than it is to 7. So we'll get a couple guesses. Let's say 6.3 and 6.4. We go ahead and we square them. 6.3 squared is 39.69. 6.4 squared is 40.96. Well, which one is closer to 40? Well, 39.69 is actually closer to 40. So our estimate for the square root of 40 is that it's 6.3. Alright, let's talk about some properties of square roots. Now the square root, because of the nature of it, works out very, very well with multiplication and with division. So we see here a property of square roots involving products. That is, that when we take the square root of a product, it's equal to when we take the square roots of two factors of that number individually and multiply those together. So the square root of 12, well, we can take the square root of 4 We can take the square root of 3 and multiply those together. Now the reason we chose 4 and 3 rather than say 2 and 6, well, the square root of 4 works out nicely. It's one of those perfect squares. So we choose the factor that's going to be beneficial to us. Now we can work this the other way. The square root of 8 times the square root of 2, well, those two individually don't work out real well. But we can go ahead and combine them. Square root of 8 times the square root of 2 is actually equal to the square root of 16, which works out famously. It's 4. So the square root of 8 does not work out well. Square root of 2 does not work out well. When we multiply them, works out great. Very, very similar thing with the quotient. If we take the square root of a fraction, usually what we want to do is take the square root of the top and take the square root of the bottom separately. So we see the square root of 25 over 16. We decide, hey, I'll split that up. I'll take the square root of 25, I'll get 5. I'll take the square root of 16, and I'll get 4. Now if we see a square root on the top and on the bottom of a fraction, we can combine those. So again, by combining them, we take two square roots that don't work out well. We combine them. 18 divided by 2 is 9. That square root works out great. Now, one great thing for me to ask for on one of our notebook quizzes would be something from this slide. Maybe I'll ask for the algebra column from this slide. Maybe I'll ask about the numbers column from this slide. Make sure you're writing this down, people. Now, when you're asked to simplify a square root, really what they're interested in doing is pulling out any perfect squares from inside the square root. So the square root of 40, which we already estimated, we're going to work on simplifying this a little bit. We know that 40 will factor into 4 times 10. Now it'll factor into a lot of different things. 8 times 5 is a possibility, but the reason we chose 4 and 10 is that that square root of 4 works out nicely. That 4 comes out of the square root, we get a 2, so the square root of 40 simplified down is 2 square root of 10. We leave the square root of 10 alone because it's not going to work out nicely. There's no other perfect squares in there, just leave it. This 2 times the square root of 10 is what we refer to as an exact answer. It's great, leave it just like that. Now, when we see two square roots multiplied together, they're probably going to want us to go ahead and multiply the two radicands. Multiply the 2 times the 18, we get 36. Square root of 36 again works out a whole lot nicer than the square root of 2 and the square root of 18 separately. Looking at similar processes with fractions, when you see a fraction in the radical symbol, you probably want to take the square root of the top and take the square root of the bottom separately. In this case, we get 7/9. If you see a square root in the top and a square root in the bottom, it's probably going to be in our best interest to go ahead, take the two separate radicands, 50 and 2, divide them, so we get 25. Square root of 25 is 5 again. Now, rationalizing the denominator. This is kind of a throwback, I'll be totally honest. This was a big deal back in my grandparents' day, your grandparents' day, when we didn't have these fancy calculators. Figuring out what 2 divided by the square root of 7 was a big old pain in the butt. So they developed a trick to get the square root out of there. Now the square root doesn't go away totally. What we're looking to do is remove it from the bottom of the fraction. Okay? We're trying to remove the radical from the bottom of the fraction. It's going to show up somewhere else. But it turns out, back in the old days, back before the fancy schmancy calculators, having a square root in the bottom was a pain in the butt. Having it in other places, not such a big deal. So we're looking to rationalize the denominator. That means get rid of the square root. So our trick here is that we multiply the bottom by the square root of 7. Now, we can't just do that willy-nilly. If we're going to multiply the bottom by the square root of 7, we have to multiply the top by the square root of 7 also. So the trick here is multiply by the square root from the bottom on the top and on the bottom. Now, the reason we do that is because the square root of 7 times the square root of 7 is 7. On the top, we have 2 times the square root of 7. We can't do anything with that, so we just leave it. So it turns out that 2 times the square root of 7 all over 7 is preferable to what we originally started with. You are expected to do this at the end of problems. You're expected to always rationalize the denominator. To be totally honest, moving ahead in math, you move on to pre-calc, you move on to calc, it's not looked upon as such a big deal. But here in Algebra 2, it's one of these things that we need to cover. It's one of these things that we need to practice. You always need to rationalize the denominator. Now, adding and subtracting square roots. We talked about multiplication and division already. Square roots get along great with multiplication and division. Not so much with addition and subtraction. Now, we can do some things. In order to add or subtract square roots, we have to make sure that the radicand, that's the number under the square root, are the same. So, when these radicands are the same, it's what we refer to as like radical terms. If we've got like radical terms, all we need to do is just combine the multipliers in front. So for our example here, 2 square root of 3 plus 4 square root of 3, since they are like radical terms, we can combine the 2 and 4 just by adding. We get 6 square root of 3. Now, what if the radicands are not the same? Well, if the radicands are not the same, then we look to make them the same somehow. So I've got 3 square root of 3 plus 3 square root of 12. The 3 and the 12 are not the same. Can I make them the same? Well, it turns out that I can. I'm going to leave that first term alone. I'm going to work on the 12. 12, as you should know by now, is 4 times 3. That square root's going to work out really great with that 4. The square root of 4 is 2. So that 2 comes out. It turns into 3 square root of 3 minus 6 square root of 3. Now that we have like radicands, we go ahead. 3 minus 6 is negative 3 square root of 3. Now, if there is no possible way for these radicands to be made the same, then we just simply don't do the addition or subtraction. If you've got the square root of 3 plus or minus the square root of 5, there's no way to make those the same. So we just leave it. Square root of 3 plus or minus the square root of 5. It is what it is. Now let's start taking a look at some examples. Again, these examples are an absolute must to your notes. Okay? Might ask for this on a notebook quiz. These should be easy points. Take these notes. Now, I see the square root of 288 divided by the square root of 8. Now my first instinct is, hey, let's go ahead, take the 288 and divide by the 8. Well, there's a slightly different way to do this. I wanted to look at this with this example. Turns out that 288 is 36 times 8. Now I'm really looking for that 8 in the 288. I separate out, because this is one of those properties of multiplication. I can take that square root of 36 times 8, make it the square root of 36 times the square root of 8. Well, look at that. Top and bottom of this fraction, I've got the square root of 8. So I get to cancel them. I've got the square root of 36, which is equal to 6. Boxed in my answers, just like you should on your homework. Let's take a look at an example where we have to rationalize the denominator. Now, the square root of 27, not a big deal. It's on the top. That's not what we're trying to get rid of. We're trying to get rid of that square root of 6 on the bottom. And that's the problem on the bottom, is the square root of 6, not the 2. Focus on the problem. Don't try to fix too much here. So I need to fix that square root of 6. So I'm going to multiply top and bottom by the square root of 6. Don't worry about the 2. It's not a problem. Let it be. Just focus on the problem. Now, on the bottom, square root of 6 times the square root of 6 is 6. On the top, I'm going to go ahead, take 27 times 6. I've got the square root of 162. Check and see if we can simplify that. Turns out, inside 162, that is a factor of 162, is 81. Why did I choose 81 out of all the different possibilities? Because it's going to work well with that square root. Bring that square root of 81 out, turns into a 9. 3 times 9 gives me that 27. Still have the square root of 2 on top. No square roots in the bottom. It's just a plain old 12. Reduce that fraction. 9 square root of 2 all over 4. Now, let's take a look at an example of adding. I wanted to jump right to the difficult ones. Got two radicans that are not the same. Can I make them the same? Well, here's a tip for you. Look for a perfect square that's a factor. I looked at 112 and I thought, what perfect square? Remember your perfect squares. 1, that's not very interesting. 4, 9, 16, 25, so on and so forth. Which one of those is a factor of 112? It turns out 16 is. Which perfect square is a factor of 63? 9 is. Look for those perfect squares that are factors. And notice what's left is a 7 in both cases. These are set up to work, people. So 4 square root of 7 plus 3 square root of 7, 7 square root of 7. Nice and boxed in. Let's take a look at more of a story problem type example. Okay, they give us this weird shape of boxes, and they tell us that the area of this shape is 40 centimeters squared. They want us to find the perimeter. Now basically what we're looking for is the length of all of the outside lines. I'm not interested in those black lines in the middle. Those are just to show us that this shape is made up of 5 squares. So that's actually my first step. I'm going to take my area, 40 centimeters squared, and I'm going to divide it by 5. Now what that's doing is finding the area of each little square. So each square that we see on the screen is 8 centimeters squared. Now, why is that useful? Because if I know the area of that square, I take the square root, and that's the perimeter. Excuse me, that's the length of one side, not the perimeter. Getting ahead of myself here. So I take the square root of the 8 centimeters squared, and that's about 2.828 centimeters. So each of these black lines is 2.82 centimeters. Well, how many black lines make up the perimeter of the shape? Well, just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2.828 centimeters times 12 of them means that the perimeter for this shape is approximately 33.9 centimeters. Now, here's our homework for the section. Again, this should not be a big surprise. I try to keep you guys informed what the homework is for the whole chapter. But here we go. For section 1.3, square roots, it's page 24, numbers 21 through 45 every fourth, 46, 47, 49, 52, and 55. So, that's the conclusion of this video. I hope you enjoyed it. I hope you enjoy all these videos. I hope you're liking this whole process. So, I'll see you in class, and I'll see you on the videos.